Welcome to the 10-minute KQL channel's Kusto Query Language Intermediate Series full course. If you're new to KQL, we recommend starting with a beginner series. The beginner series will help you form a strong foundation of KQL knowledge to build on. These are all the operators previously covered in the beginner series. The intermediate series layers on additional skills to help you become more functional in the language beyond the basics. This full course gives a short explanation and at least one example per concept. After you've learned the material, you can use the video timeline chapters to quickly go back and refresh on a topic that you haven't used in a while. If you want more in-depth instruction with additional use case examples, review the Intermediate Series playlist on the 10-minute KQL channel for 10-minute long videos with homework challenges to get hands-on practice for each operator type. Once you've mastered the intermediate level concepts, we recommend progressing to the Advanced series, which focuses on parsing JSONs, manipulating string data, working with functions, regex, and other useful tips to help you master KQL. In the future, we'll make a security analyst playlist to help new security analysts with best practices and tips. If there's any additional topics you're interested in learning, please let us know in the video comments below. In this full course, we'll be using free data sets in Azure Data Explorer, or ADX, found at kc7cyber.com. This is a free cybersecurity-focused site that uses data sets simulating compromised companies so you can practice your KQL skills during an investigation. Let's get started by discussing summarizations. Summarizations are great for answering big-picture questions about your dataset. They're useful for investigations, and they also facilitate presenting your information in charts and graphs. In the beginner series, we learned to use distinct to identify unique values in a given field. In this example, we're looking at authentication events. If we wanted to see the unique result types, we could use distinct in this way. Here we see that there are only two distinct result types for authentication. We can change distinct to summarize to help us enrich this data. There are many functions we can use with summarize to help us with the enrichment. Here we're adding a count function for each result type to enrich the distinct values. In this case, we placed our enrichment function to the left of the by and the fields we wanted distinct values of to the right. If we want to summarize by more than one field, such as a result and username, we can place additional fields to the right of by. Each count is of the unique combination of both fields. We can also layer in multiple functions to enrich our data. We can add the earliest and latest date-time values for each username and result type. We can see that the first user has a total of 17 failed login attempts from August 13th through September 9th, and they had 24 successful sign-ins in the same period. We can also layer in the make_set function to list out all the IP addresses associated with both failed and successful authentications. This can help us identify any potential anomalies in the login activity. We can use the dcount function when we need a distinct count of unique objects in a given field. The count field on the left is saying this user had 24 successful logins. The dcount field is saying there are 2 unique IPs associated with successful logins for that person. You can start to see how powerful summarizations can be in answering questions we have in our dataset. In our query, we have min and max time values. We may have a series of records, but only want the most recent record for each day. And we don't need the other values represented. The argmax function can help us out. In this example, it shows us the most recent successful and failed login for each username. Argmax requires 2 arguments. The first is the field you want the target for the time value. And the second is what fields you want to display. If you choose the asterisk, you'll display all available fields. If we only need the timestamp, host name, and username fields, we could just type them in, just like we would be using in Project. We also want to introduce the bin function. In previous queries, we provided enrichments for a wide range of time domains. We can also place the time values into buckets of 1 minute, 1 hour, 1 day, 1 week, or any other time bucket we choose. Let's narrow our focus to the first user. Our goal here is to identify how many sign-ins occurred each day. We can use the bin function to break the summarized count by day, like this. We can see that the activity took place on 4 distinct days. The bin function wants 2 arguments. The first is the field to create the bin buckets in, and the second is how much time each bucket should represent. If we wanted to visualize this data in charts and graphs, we could use render. We see there are many types of charts and graphs to choose from, so let's pick time chart. We can see it plots the number of login attempts by day. If we wanted to add additional resolution, we could change the bucket size from 1 day to 1 hour. This shows us a more precise window for the activity. We can also look at this data in different chart and graph types. Lastly, we can use the countif function if we only want the count under certain circumstances that we define. In this case, it will only provide a count if the result is a successful login. Let's move on to the topic of variables. Variables lock in a value or even an entire subquery into memory for the life of a query. The same variable can be used multiple times in the same query, but can only be called after the variable is declared. To create a variable in KQL, we use let. We then define the name of the variable. The name should help you or others understand what the variable represents. Good code reads like a book, and you can look back a year from now, having forgotten exactly what the query intended to do, and easily understand the output it produces. When you name your variable, avoid using names of existing fields. Some people like to place an underscore before the variable. Others like to make the first letter lowercase and other descriptive words uppercase. Pick a method that works for you and take a look at how others write their queries. Let's go back to one of our previous queries. If we wanted to filter for distinct counts of 3 or more, we could just place a where line, like this. Let's take the value of 3 and make it into a variable. Remember to add a semicolon at the end of the variable, which locks it into place. Now replace the number 3 in the where line with the variable name. You can see that once the variable is set, it displays as an option in IntelliSense. When we run the query, we see the results haven't changed. Now let's modify this query to see only exact values of 3 distinct IPs. We can see something unusual. The devices that are not local admins are being authenticated to by the same IP addresses beginning with 104 and 87. If we get rid of the local admin devices, these authentication events need to be investigated more. If we need to take this data and reference other tables, we have a couple of options. We can join the 2 tables, or we can use techniques called chaining and pivoting. Let's say we want to take the user names from this data set and pivot to employees table, so we can see more information about these 7 employees. First, let's use distinct to provide a single field with nothing but usernames. Now let's set this entire query as a variable. We created a variable called users, and we placed the semicolon at the end of our query. To make sure this variable works, we can simply call the variable on the next line to test it out. Perfect, it provides us the list of 7 users. Now let's go to the employees table. Let's make a where line that filters for usernames that are in our variable. We can use in, then place the name of the variable in parentheses. In this case, in is like using an or statement. So if any values in our variable are true, the record will display in the output. We can see the roles of these individuals are all network admins or operation managers. This activity is still suspicious to us, so we may want to pivot another time to identify activity on each device. We can use distinct to identify each host name. Then we can set this subquery as its own variable as we move to the next table to look at device activity. We can see that all 7 devices have the same discovery commands performed that an attacker may use for lateral movement during an attack. We definitely want to look at activity for these 7 devices more carefully. We can see that chaining multiple let statements together as we pivot from one table to the next helps us branch our investigation and dive deeper into multiple areas of new discoveries. If we have a variable that contains multiple values, we can use packarray. If we want to see if any of these values are found in a field using delimiters, we can use hasAny. If we wanted to see how many devices had all 5 of our discovery commands in the process command line, we can use hasAll. In this case, none of the 8 devices had all 5 discovery commands in their command line. If you find this content valuable, please give the video a like. And if you want more KQL content, click the subscribe button with the notification bell. Let's transition to joins. When we have 2 tables that we want to merge on a similar field, we can use joins. The common field is called a key. Let's show a basic example of a join so you can visualize the concept. The email table shows inbound and outbound emails. We know the employees table shows details of each employee, including their email address. What if we want to enrich the email table with additional information like the sender's device, IP, or role? In this case, the common field on both tables is the email address. Let's just focus first on the sender field of the email table. When we look at the employees table, we see the email address field name is email_ADDR, which is different. We can still join these 2 tables in this situation. If we're only interested in adding a few fields from the employee table, we can first start off by writing a query that displays only the information we want to join to the email table. Now to join this data with the email table, we use join. Then add the name of the second table in parentheses. Then we type on. After on, we define the key that we want to join on. If the field names in both tables are the same, we can simply type it in. But if they're different, like in this case, we define the field name of the first table, then the field name of the second table that will be used as keys. When we join, the first table we introduce is referred to as the left table, and the second table we introduce is referred to as the right table. So in this case, employees is the left table, and email is the right table. Let's run this query and see if the join worked. We can see that all the emails sent by our employees with the enrichments of the IP address, host name, and role information. This is a useful tool for collecting all the information you need in one place, so you can manipulate and filter it more effectively. There are many kinds of joins, and changing the type of the join will often change the output of your query significantly. The best way to visualize joins is to use a Venn diagram. KQL has 4 primary join types: the inner, outer, semi, and anti-join. Inner joins show results for key matches. Outer joins show key matches, but also show records that are not a match on one or more table that we define. Semi-joins first match the keys, then only show matched records from one table. Anti-joins first match the keys, but only display records that are not a key match. Each primary category has subcategories. The inner unique type is the default in KQL. It first deduplicates records on the left table and then displays key matches from the right table. If we don't define a key type in our query, like in the previous example, KQL will default to the inner unique join type. The inner join shows all records from both the left and right tables with a key match, and it does not deduplicate any tables. The inner join type is the default type in the SQL language. While inner joins only show records with key matches from both tables, outer joins show the key matches and include records that are not matched. There are three types of outer joins: a left outer, right outer, and full outer. A left outer will show you all the inner matches, plus add records from the left table that are not a match. A right outer will show all inner matches, plus add records from the right table that are not a match. And a full outer will show all records with matches and records from both tables without a match. A semi-join first calculates key matches in the same way as an inner join type, but it then discards values from one of the tables of choosing. A left semi-join starts with all the inner key matches from both tables, but it only shows the matching key values from the left table. A right semi-join starts with all the inner key matches from both tables, but only shows the matching key values from the right table. This is handy if you don't have a need for joining two data sets and only want to work with one table, but you want to identify the matches from a second table. Lastly, we have an anti-join. Anti-joins are similar to a semi-join in that they only produce records from one table. But instead of showing records with key matches, the anti-join only shows records that don't match. In a right anti-join, first all key values are matched. Whatever is remaining from the right table that is not a match is displayed as the output, with the opposite for the left anti-join. The anti-join is great for identifying all the outliers that don't have a key match. It may be hard to understand use cases for each join type, so we'll run through a few examples. In our first example, we have our employees table, which shows IPs for each device, and we have outbound network events that also has IP addresses. If we only want to see the outbound network traffic from devices not directly assigned to individuals, we could use an anti-join. In this case, we place the employees table first, so it's our left table. We place our outbound network events table second, so it's our right table. We can place kind equals, then define the join type. In this case, we want to use a right anti, which will show us records only from the outbound network events table that do not match with IPs listed on the employees table. On the next query, we have our employees table and our net flow table that shows network traffic logs. We want to first match network source traffic to all of our employee devices, but only display net flow from the matches. And we don't need to see any data from our employees table. In this case, a semi-join would be best. If we change the kind to right outer, we can see the number of records changed. And also some fields on the left are blank. Those represent records that did not have an IP match on the employees table. But since it's a right outer, all of the non-matches on the right table are still displayed. If you have multiple cloud tenants and you have the same tables in multiple tenants, the union is perfect for merging them in a single place. As an example, if you want to merge sign-in logs from one tenant with sign-in logs from a second tenant, the union would be the best option. Also, if you wanted to merge interactive sign-ins with service principal sign-ins, you could use a union. If you chose to union on two tables that do not have the same general schema, you'll have many blank cells. As an example, if we wanted to union device process events with file creation events, so we could have a unified sequential timeline of all processes executed on a device next to the files that were created on the device, we could union those tables. This can also help us in our investigation if we filter down to a narrow time frame of known malicious activity. We could see which files were created as a result of processes executed. Sometimes we need to export our output into a CSV file. We can do this using export to CSV, so we can manipulate the data in other programs. We may also want to bring in data from external sources. To do this, we can use external data. In this example, if we go to the following website, we can see a list of Tor nodes. In this example, we want to see if we have any inbound traffic from one of these nodes. First, we can create a variable using external data. We know from looking at the data that it's a single field of IPs, so we can define the field name as IP and cast it to a string data type. We then place brackets and use the @ symbol, then place our URL in quotes. We finalize our let statement with a semicolon. Before we go any further, let's call our variable and make sure it pulls the data without errors. We see it worked with over 1,000 IPs. Now let's pull up our inbound network events table and see if any IPs are in our Tor list. We don't see any of the IPs in our list, which is great. But this may be an alert we want to set and be notified of if any positive hits occur. Let's transition to data types in KQL. We'll refer to our data sets with fields running in vertical columns and records running in horizontal rows. We can use getSchema to identify the data type of each field of the table. Even though the data types are defined, we can change them as needed to help us answer questions. There are limitations on what you can do with some data types, and other data types open new functions and capabilities to more easily perform tasks. Here's a list of the KQL data types. Bool is short for Boolean, which refers to a field that either has a true, false, or null value. You may want to write a query with a true-false value for a certain condition. In this example, we're looking at an email table showing inbound and outbound emails of the fictitious company. We'll extend a new field titled isExternal that will first look at the subject line, and if it begins with external in brackets, it will be defined as true. The date-time data type represents an instance of time. Although it's normally expressed as a date followed by a time, it could just be the date or just the time. Keep in mind that Kusto's default is to display in UTC, so if you need a specific time zone, generally it should be changed. If you want to review date-time options in depth, review to Lesson 9 of the Beginner Series. The decimal data type is a 128-bit length decimal number. While this is an available data type to use, it's more common to see decimals used in a real data type. The decimal data type is more precise in math equations than other options, but it's slower in processing time. So it may be a better option when precision is important and in niche use cases. The dynamic data type is unique in that it can take on any of the scalar data types such as bool, int, long, reals, or strings. JavaScript object notation or JSONs, which are displayed in key value pairs, are often represented as a string data type. And to more easily manipulate the contents, we change them to a dynamic data type. Sometimes they're stored in the database and they're already in a dynamic data type. So it's best to look at the data type before manipulating these types of objects. Deciding to switch to a dynamic data type can unlock additional capabilities in our queries, but it can also restrict the use of some operators and functions. So switching to dynamic has pros and cons. As an example, using distinct and summarize will throw an error if used on fields with dynamic data types. We'll be discussing parsing and manipulating dynamic objects in the advanced series. The GUID data type isn't very common in KQL, but it represents a globally unique identifier represented like this. Oftentimes you'll see GUIDs simply represented as string data types. When we think of numbers, they can come in many forms. We already talked about the decimal data type. Another data type for whole numbers is an int, which is short for integer. The int type is 32 bits in size and represents whole numbers without decimals. If there's a value with decimals and the data type is set to integer, it will round down to the next whole number. For larger whole numbers, you can use a long data type, which is 64 bits in size. While you see long data types more often than GUID data types, they're still not used that much, unless it's a specialty use case that requires them. Real data types are also 64 bits in size, but they allow for a decimal point, and may be more commonly seen over a decimal type. The most common data type is a string. It can represent a sequence of Unicode characters. Individual characters in a string can be letters, numbers, and symbols. Strings are placed in quotes. KQL has special characters that can't be used inside of a string. As an example, if you want to use a quote as part of a string, normally it would be recognized as the end of the string. We can use escape characters so it becomes part of the string literal. As an example, I want to print KQL is very intuitive, but I want intuitive to be surrounded by quotes when it prints. If I use a special character, such as a quote in a string, I use a backslash as an escape character to make it part of the string output. Time span data types measure the length of time between two time markers. If you have two different time fields in a query, and you want to identify the difference between the two, the output will be in a time span format. This can be useful if you want to identify how long ago something happened from the time the query ran. Sometimes the field has a record with no values in it. If the data type is a string, then the field is considered empty. If the data type is anything other than a string, the field is considered null in KQL. In this example, we're creating a new field called isempty and using the isempty function to identify a Boolean true-false value, whether the verb field is empty or not. You can also use isnull depending on the data type. There's also functions for isNotEmpty or isNotNull, depending on your use case. Casting is a term used when we change from one data type to another. We may do this so we can perform a math problem, or it may be so we can use a special function that only works with a particular data type. Sometimes we cast to one data type so we can manipulate the data, and then we cast back to the original data type to present it. When we cast to a new data type, we typically use this general format. Keep in mind that there are additional functions like parse JSON that don't follow the typical formatting, but they also cast to a different data type. In this example, we're looking at the network flow data for a fictitious company. When we look at the schema, we see a mix of date-time, string, and integer data types. If we wanted to change the bytes field to a string data type, we can cast it like this. And when we look at the schema again, we can see that it changed from an integer to a string data type. That's all for our intermediate series full course. If you want more examples and more in-depth descriptions of each operator, review the 10-Minute KQL Channel's intermediate series playlist, which has 10-minute sessions on each topic covered. When you're ready to move on to parsing JSON objects, manipulating strings, and building functions, check out our advanced playlist. If you have any suggestions for future content, please let us know in the comment section below. If you find value in these videos, please support the channel by hitting the like button. And if you want to receive notifications of new videos, hit the subscribe button with the notification bell.